Well, here we are with voltaic cells. This is probably where we've been trying to get this whole time. Voltaic cells are batteries, okay? So pretty much this is the principle under which all batteries operate. The lithium-ion batteries in your phones all rely on redox chemistry, the batteries in your laptops and everything like that in order to be able to operate. And they operate by having a flow of electrical charge. So we're going to go through how to describe a voltaic cell, how to set one up, the key components of a voltaic cell, how they produce electricity, and also how they produce or the amount of voltage that they will produce. Essentially, we're still using this idea of redox, that the reducing agent always loses electrons. It reduces the oxidizing agent and therefore undergoes oxidation. And the oxidizing agent accepts electrons, oxidizes the reducing agent, and undergoes reduction. So essentially, in order for a cell to work, we need to have a reducing agent and an oxidizing agent present so that we can generate the electrons and then transfer them to the oxidizing agent. If you think back and you recall this reaction where we had the copper metal in silver nitrate solution, and eventually we saw the formation of copper nitrate and silver metal, this, if you remember, was a spontaneous redox reaction. Just put the copper in and the reaction started to go straight away. There was no delay. There was no need for us to get it started, to ignite it, or anything like that. The reaction occurred what we refer to as spontaneously. So if we have a closer look at this, we can see that what's actually happening is the copper is being oxidized. Okay, and the nitrate and the silver ions are all in solution. So we've got our piece of solid copper here, and then we have our solution of silver nitrate, all as dissociated ions. So then what happens here is that the silver comes into contact with the copper and the electrons are transferred from the copper onto the silver. As that occurs, silver becomes an uncharged solid metal, so it will precipitate out of solution. And the copper 2 plus, it's lost 2 electrons, so it becomes charged, and copper is soluble in water. So this charged ion therefore pulls off the surface and is going into solution, which we see by the blue color. This piece of copper degrades over time, is eroded away, and then we see the buildup of silver onto the copper wire. So we know, looking at this reaction, that something's happening. Okay, we have a transfer of electrons, but it's not very useful if we just have this reaction going on in solution, where, same as this zinc rod here, the zinc is placed into copper sulfate solution. In this case, because the zinc is more reactive than the copper, the zinc is eaten away, and we get a formation of a copper precipitate. Okay, so we can do this. The reaction is spontaneous, but it doesn't seem very useful. Okay, but if we separate the aspects of this, turn it into 2 electrodes, then what we can do is we can actually force this electron transfer to occur via a wire, like this picture over here. So the electrons now are being generated in one electrode, transferring through a wire, and then being consumed at the other electrode. And that movement through the wire is what creates our electrical charge. So essentially what we get is that we need a spontaneous redox reaction, and this will generally produce heat. It produces energy, so it's an exothermic reaction. But if we separate the 2 half cells, now that the copper and the silver would not be in contact, then what happens is that if we connect these by a wire, that electron transfer still wants to occur, but it has to the electrons have to travel along the wire in order for that to happen. So the electrons will travel along the wire, and when electrons travel along a wire, we get a flow of current. Okay, so our electrons always run from the anode to the cathode. Okay, so they run from, and if you remember any of your physics, your anode is negative in a battery and your cathode is positive. So we get a transformation into electrical energy as we force these electrons along the wire for the redox reaction to occur. And we can see this happen by actually separating the two reactions into two separate beakers. Okay, so we have a solution of the electrolyte. So if we have copper solid, like we do on this side, then we will have that with a mixture of copper 2+. Now it could be copper sulfate, copper nitrate, or something like that. The other anion has to be one of our ones that tends to be soluble and doesn't form precipitate. And then if we have zinc over here, we would have the electrode being made zinc solid and Zn2+ in my solution. Okay, again, just like we mentioned in the last video, these would be at SLC. Okay, so these are standard laboratory conditions. So our solution is 1 molar and it'd be 1 atmosphere pressure and 298 Kelvin. If we do this, then the electrons pass through here, and if I have a light globe, it would glow. Okay, so we need to split the two half reactions of a spontaneous reaction in order for us to generate electricity. And when we do, we get what we call a cell. Okay, and when we have multiple cells, we have a battery. So this is a schematic of it drawn with everything labeled. So we have a copper strip in copper sulfate solution. So it's a dilute solution of copper sulfate. It would be 1 molar. Okay, and a copper strip connected by an external wire to a galvanometer, which is checking our electrical current, or it could be a light globe, down into a zinc strip, which sits in zinc chloride solution. And then we have this salt bridge, which usually has a solution of KNO3 aqueous, because if you remember, potassium salts are always soluble, nitrate salts are always soluble, so if they come into contact with any of the components in each beaker, then they wouldn't produce a precipitate. So this cell where we have copper and zinc, we actually refer to as a Daniell cell. Okay, so it's an archetypal galvanic cell that is made with copper and zinc. So if we look more closely at each half cell, okay, we have zinc and copper, and if we look at an electrochemical series, we know that zinc is more reactive than copper. So because zinc is more reactive than copper, it will oxidize, and then copper will be reduced. So essentially, we're having that displacement reaction, but occurring in two separate beakers. So the zinc will undergo oxidation, generating electrons. The copper will undergo reduction. So as the zinc is oxidized, the electrons are now going to be generated in the zinc electrode and will be pulled along the wire. They will end up down here, and the copper 2+ will be reduced onto this electrode here, which is the site of reduction. So zinc is oxidized at the electrode where oxidation has occurred, and this is the anode. Okay, so oxidation occurs at the anode and is the negative electrode. And if you think about that, what's happening here with oxidation is we're generating a lot of electrons. So if we were to freeze time instantly and have a look at this electrode, it would have an excess of electrons, so it would have a negative charge. The electrons then flow through the external circuit down into the copper electrode. And what happens there is that the electrons are sucked up and used by the copper to form copper solid. So if you think about it, again, freezing time, the electrons are being used up. So if we look at it at any one particular time, this will appear to be electron deficient, having a positive charge. And the positive charge is the cathode. Okay, remembering that cations are positive. Okay, so we've got the cat and the cathode. Okay, so we have the redox pair of zinc and Zn2+, and then the other redox pair, copper 2+ and copper solid in our cell. So the electrons will always flow towards the cathode, which is the positive electron. And then remember how I said we had those KNO3 ions in the salt bridge? Well, what will happen is because we're using up positive charge in this cell over here, we need to balance that out. So the K plus ions will move out of the salt bridge into solution to balance out that loss of positive charge. Otherwise, if you think about it, we've still got our sulfate ions in here, and if we didn't balance out with more positive ions as the copper got reduced, we would get a buildup of negative charge in that half cell. And if it built up to negative charge, then the electrons wouldn't flow because they wouldn't flow towards a negative solution. So it's essentially to keep the net charge zero and close this internal circuit, because the other thing that can happen is that this flow of ions is now essentially forming the circuit. It's not electrons, so the electrons flow into the electrode, and now in order to complete this circuit so that the electricity will flow, it changes to a flow of ions. So this is just a closer diagram that is annotated for you with our cathode being the positive electrode, anode being the negative electrode. A reminder that oxidation occurs at the anode, reduction occurs at the cathode. When we draw these, we label them with our half cell equations, the net reaction, and then also we should put what our salt bridge is, which is what we call the solution of KNO3. And then this diagram on the right gives you a close-up of what's going on in that our copper 2 plus are being deposited. So this electrode will actually get larger in size, okay, as the copper is deposited onto that electrode. And then our zinc anode here, the anode tends to get worn away. It becomes pitted and wears away. So these are the definitions of each of the things that we need to be able to do. So we need to know definitions of each of our terms. We have the electrode, which must be a material where there are delocalized electron presence that can move through the circuit. The electrolyte is our solution made up of aqueous dissolved ionic compound, and the cation must be the same as the metal that we're using. Half cells contain the separate oxidation and reduction reactions present in our cell, okay, and each half cell contains an electrolyte and an electrode. The internal circuit is formed by our salt bridge and allows the flow of ions between the two half cells. Our external circuit is the connection between the anode and cathode, which is generally a wire with a globe or voltmeter in the middle. Our cathode is the electrode where reduction occurs, and we can remember that by red cat. Okay, remember we had oil rig is oxidation is loss, reduction is gain. Now we have red cat and anox. Reduction always occurs at the cathode, and the oxidation always occurs at the anode. That is a rule. There's no exceptions to that one. Reduction always occurs at the cathode, and oxidation always occurs at the anode. And then we have the salt bridge, which is our electrolytic conductor that completes the circuit between the two half cells and keeps the net charge in each half cell zero, with cations moving towards the cathode and anions moving towards the anode. Okay, so this is just a little picture for you to remember that we have anode, which is oxidation, so anox, and red cat is reduction at the cathode. Just a couple of notes on the salt bridge quickly before we go to our example. It is important to remember the role of the salt bridge, and we must show it when we draw our diagrams. The other thing to make sure is that your level of electrolyte solution, the salt bridge and the electrode are in contact with the electrolyte at all times. But essentially, we've talked about this where the anions will move towards the anode and the cations will move towards the cathode in order to stop that charge building up in the cell. There are another ways that we can show cell convention, and that is to we always draw the anode on the left, cathode on the right. We use a double vertical line to dictate a salt bridge, and then a phase boundary, i.e. this is solid and aqueous, between the electrode and the electrolyte. We tend to not draw these in exams, but we do need to be able to recognize them if something like this was shown in an exam question. Okay, so the potential difference is the amount of electricity or the amount of electrical current that will be produced from a galvanic cell or voltaic cell. so where the electrons are moving from the anode to the cathode. Okay, and this is because there's a difference in potential energy between the two cells. Okay, we've talked about potential energy. So there's a difference in electrical potential energy. That electrical potential energy is given as the E0 value you see printed on your electrochemical series. And that value, okay, that value is measured against our hydrogen electrode. For standard level, we don't need to do any calculations with it, okay, but you can see that the more reactive metals have a more positive cell potential. So essentially what we do need to know, though, is that the further two things are apart, the distance between them, the difference between them, the greater that is, the greater the potential difference that we will see in our cell. Okay, so the further two things are apart on the electrochemical series, the greater the voltage that will be produced by that cell. So if you have a look where lithium is on your electrochemical series, you can understand why we use lithium for high-powered devices. Okay. So this is an animation that you can watch on the electrochemical series. I'm not going to play it here just because it'll take up a bit too much time. So essentially we need to be able to draw these. This is a diagram here, but you should be able to draw these by drawing the individual half cells and the salt bridge. It is important to remember that we also annotate the polarity of the electrodes, i.e. showing whether it is positive or negative, and that this will be the cathode, this will be the anode. You should also write the two half equations are going on in each half cell. So you should put the equations and annotate yours with the equations, and always state what is in your salt bridge as well. Okay, so these are the kind of diagrams we need to be able to draw. So let's have a look. We have been given a cell here between lead and nickel, and we have to label the anode, the cathode, the flow of electrons, suggest a suitable solution for the salt bridge, and the flow of ions, write the half equations associated with each half cell. Now, I don't actually have an electrochemical series with me here, but let's have a look. Now, it is, if I remember from memory, and please correct me if I'm wrong, nickel is the more reactive metal and lead is the less reactive metal. And if I go by conventions, this is always also on the left-hand side. So nickel solid should be, this should be my anode, this would be my cathode, and you would check this on your electrochemical series to see which one was more reactive. So from the anode, I'm going to be generating electrons. So my electron flow will go from anode to cathode, which means that I have now identified the anode, I've identified the cathode, I've shown the flow of electrons. Suggest a suitable solution for the salt bridge. Well, potassium nitrate is pretty much our great salt bridge. Okay, show the flow of ions. Well, we will have Pb2 plus being reduced to Pb solid. And in that case, we will have potassium ions coming down out of the salt bridge. We will have nickel solid going into nickel 2 plus, and then we will have nitrate anions coming down into the solution to balance that charge. And then write the half equations associated. So we would have nickel 2 plus, plus 2, whoops, wrong one. This is the anode. So we're going to have oxidation occurring. So nickel solid goes to nickel 2 plus, plus 2 electrons. And then on this side, we will have Pb2 plus aqueous plus 2 electrons is going to go to Pb solid. And there we have a fully annotated diagram. Let's have a look at one with a worded description. So we've been asked to draw a voltaic cell, and you'll notice that the term voltaic or galvanic cells are used interchangeably, and we'll get to that. From zinc and lead and their respective ions, given that the zinc is a stronger reducing agent, so remember the reducing agent is always oxidized, So this is going to be my anode, then the lead, which will be my cathode. Draw a diagram, fully label it, showing half equations, the polarity of the electrodes, and the direction of flow. Okay, so I'm going to need 2 half cells, a salt bridge, an electrode in each side, a voltmeter down to here. I'm going to need my electrolyte solutions up high enough to go past my electrodes. And then I'm going to have possibly lead nitrate in my electrolyte. And oops, that's going to be my cathode. So let's follow convention and just put it over here. So this will be lead nitrate. This is going to be, we can use zinc chloride in my anode. This will be my anode. Cathode. Again, I know this because zinc is the more reactive metal. So zinc solid will be going to Zn2 plus 2 electrons. And on this side, Pb2 plus 2 electrons will be going to Pb solid because the cathode is always the site of reduction. I will have KNO3 in my Schultz bridge. My electrons will flow from anode to cathode. This will be zinc, and this will be lead. Have we got everything that we want? Oh, and potassium and nitrate ion. So potassium will flow towards the cathode, nitrate will flow towards the anode. And there we have it. That's our diagram of a galvanic cell gone through from a description. Okay, this video is getting pretty long. This is just a little bit of extra information if you want to have a look at how some of the original batteries were made. So essentially, depending on, if you talk to the VCE kids, and please don't in terms of looking at studying redox together, but they will tend to refer to things as galvanic cells. In IB, we tend to call them as voltaic cells. But essentially, Alessandro Volta, Luigi Galvani came up with very similar systems at around the same time. So Volta is who Volts is named after, okay, and then galvanic cells are named after Galvani. So if we look at Galvani's, he pretty much came up with the zinc and copper reaction that we look at in detail. Volta first looked at actually passing electrical charge through frog's legs and noticing that they twitch. So we're looking at how electrical impulses are travel along through nerves. But he originally thought that this was due to a particular kind of animal electricity, but his studies later on showed him that this was not the case. So you can watch these videos about their discoveries and how their batteries work for interest's sake. But that's all that we have, and I know this is a long video, but thank you for persisting. So if you've taken good notes, have a bit of practice at drawing your voltaic cells using the electrochemical series to determine the anode and cathode, remembering the more reactive metal will be the anode because that's the site of oxidation. That we can produce electrical energy by separating these two spontaneous half reactions. The general features, so have all those definitions written down for your electrodes, electrolytes, salt bridge, and understanding that the voltage set up in a voltaic cell will depend on the difference in the reactivity of two metals. So for SL, that's just knowing that the further they are apart on the electrochemical series, the greater the voltage that they will produce. Okay, so that's it. And remember, we will make sure we practice some of these cells.